Hello and welcome to 1.4, Continuity and One-Sided Limits. Continuous, be a graph with no breaks, holes, or skips at a particular point C. If it's continuous at C, it doesn't jump, doesn't have holes, doesn't skip. Examples of discontinuous graphs. Here's one that's discontinuous because there's a hole at C, so f of C is not defined. Here's one where our limit at C does not exist because this graph, as you approach, I should say at B does not exist. Or should we call this C and this B? Anyway, going from the one direction you have one value, the other direction you have a different value. So it's not continuous there. And here is one where the limit as x approaches C of f of x is not actually equal to f of c. So here's the limit is trying to go to this value up here, but the actual defined value is down lower. So continuity at C can be destroyed by any one of the following conditions. First, the function is not defined at C, as we saw. We've seen that one. Second, the limit of f of x does not exist at C. Might be going to two different places. And third, the limit of f of x exists at x equals c, but it's not equal to the actual value of f of c. That was our third case. If none of the above conditions is true, the function f is called continuous at c. Here's the definition of continuity. Continuity at a point. A function f that's continuous at c if the following three conditions are met. F of c is defined, and the limit as x approaches c of f of x exists, and the limit as x approaches c of f of x equals f of c. So f of c exists, it has a limit there, and the limit is equal to f of c. That would give us continuity. Now, continuity on an open interval. A function is continuous on an open interval, a, b, if it is continuous at each point in the interval. A function that is continuous on the entire real line from negative infinity to infinity is everywhere continuous. If a function is defined on an open interval I but is not defined at C, we say the function has a discontinuity at C. And there are two categories of discontinuities, those that are removable and those that are not removable. A discontinuity at C is called removable if f can be made continuous by appropriately defining or redefining f of c. Like if you could factor out a discontinuity. So discuss the continuity of each function here. So this first one, this is a non-removable discontinuity. Because 0, there's no way to get rid of that. Add 0, this is not continuous. Next one, g of x equals x squared minus 4 over x minus 2. So as this sits, this is not continuous at x equals 2. But this could be written as x minus 2 times x plus 2 over x minus 2. Then our x minus 2's can divide out, leaving us with x plus 2. So this has a removable discontinuity. At x equals 2. I should say at x plus, at x minus 2 equals 0, so x equals 2. The last one, h of x equals x squared, x plus 2, for x being less than or equal to 0, and it's x squared plus 2 for x being greater than 0. What we're seeing here, we have a graph here. And then x squared plus 2, that's a parabola, and it's defined just up to but not including 0, but that happens to coincide with 0, 2 from here. So So this is continuous on the entire real line. There's no skip. They happen to match right up. So because there's no gap in this, it just goes up and then picks up right there and keeps on going, it is continuous, even though it's a piecewise function. Okay, I'm going to go on to the next page, so feel free to pause if you need to pause this one. We're going to talk about one-sided limits and continuity on a closed interval. Okay, so one-sided limit, that means limit from the right or a limit from the left. Now this notation is really important. Limit from the right. X approaches C from values greater than C. We show X going to C with a little plus there. So you might need to look at your notes to see that it's a really small, little plus on the right side. It looks like a power, but it's not. That means C from the right side. That means limit of f of x as x approaches C from the right side equals L. Limit from the left side, so going from the left side means x approaches values of C, approaches C from values that are less than C. Now being less than C doesn't mean they're negative, and over here doesn't mean they're necessarily positive, but we have a negative power up here. It looks like a power, it's not a power, but it means you're from the left side. So a negative means you're on the left side of that value, positive means you're on the right side. But the power looking thing does not indicate if it's a positive or negative value. Okay, find the limit if it exists. Limit as x approaches 2 from the right side of 2 minus x over x squared minus 4. That's going to be the limit as x approaches 2 from the right side of negative 1 times x minus 2 over, and you could factor x squared minus 4 to be x minus 2 times x plus 2. These divide out. You have the limit as x approaches 2 from the right side of negative 1 over x plus 2, which becomes negative 1 over 2 plus 2, negative 1 over 4. So our limit exists. And just to get a visual on this graph, we have a vertical asymptote where this denominator x plus 2 is 0. That's at negative 2. So our graph with a negative 1 on top, I believe would look more like this. In my notes I have this backwards, but this is what it's going to look like. And you'll have a hole right here. Okay, one-sided limits can be used to investigate the behavior of step functions. If you remember step functions from pre-calculus, they look like steps, the least integer function. Or I should say the greatest integer function being the greatest integer less than or equal to the number given. So one common type of step function is the greatest integer function. Has these double lines on each side of it. That means greatest integer n such that n is less than or equal to x. So the greatest integer of 1.5 is 5. The greatest integer of 2 is 2. That's where it steps up, is at the integers. So example 3 says find the limit of the greatest integer function as x approaches 1 from the left and from the right. Well, if I look at this graph, graph of this is going to be solid 0 going across to that. That means up to like 0.5, 0.6, 0.7. The biggest integer less than or equal to those is 0. Then at 1 we jump up to 1. We're talking 1.1, 1.2, 1.3, 1.4, 1.5, all the way up to 1.9999999. Once you get to 2, it jumps up here. So it makes those steps. Likewise back here. So the question is, find the limit as x approaches 1 from the right side that means you're going to 1 from the right side. That limit's going to be 1. And we'll find the limit as x approaches 1 from the left side. And that's going to be what? Well, that's down here on the left side of 1. It's over here. That's going to 0. So given that the limit is different from the right and from the left, this limit does not exist. Probably get a little ahead of myself there. Okay, feel free to pause that. Get ahead of myself because the next thing is the existence of a limit. Let f be a function, let c and L be real numbers. The limit of f of x as x approaches c is L if and only if the limit as x approaches c from the right side of f of x is L, and the limit as x approaches c from the left side of f of x is L. So if the limit is the same from both directions, then the limit exists. Next one, definition of continuity on a closed interval. A function f is continuous on the closed interval ab if it is continuous on the open interval ab. So the open interval that does not include the endpoints. And the limit as x goes to a from the right side of f of x equals f of a. And the limit as x goes to b from the left side of f of x equals f of b. So as long as the limit is going to be the same as the defined value, then it's going to be continuous on the entire interval. So the function f is continuous from the right at a and continuous from the left at b. So discuss the continuity of the function on the closed interval. So talking g of x is equal to the square root of 25 minus x squared on the interval from -5 to 5. So 25 minus x squared is greater than or equal to 0 because it's a radical. So the domain of G is the closed interval from -5 to 5. So at all points in the open interval -5 to 5, the continuity follows the limit of a function involving a radical. Okay, so what this is saying is we're good on the open interval. We're good. It behaves like a radical should behave. The limit as x approaches 5 from the left side of the square root of 25 minus x squared is 0, and that is g of 5. And the limit as x approaches -5 from the right side of the square root of x squared, 25 minus x squared, is going to be 0, which is also g of -5. So we can conclude that this is going to be continuous in the entire interval. At f is continuous on the closed interval from -5 to 5. Okay, the next thing. Properties of continuity. If b is a real number and f and g are continuous at x equals c, then the following functions are also continuous at c. The scalar multiple, b times f. The sum and difference, f plus or minus g, product f times g, and the quotient f over g if g of c is not 0. Let's scroll this up a little bit. So pause if you want to keep working on that example. The following types of functions are continuous at every point in their domains. Polynomial functions. Got a polynomial there. Rational functions, as long as the denominator is not 0. Radical functions. And trigonometric functions. Okay, so example 5 says, are the following continuous at every point in their domain? Well, what we just saw, polynomial, trigonometric, so this is yes. Trigonometric, yes. It's going to be continuous at every point in this domain. Polynomial, yes. What we just saw said each of these are going to be continuous at every point in their domain. Okay, continuity of a composite function. If g is continuous at c and f is continuous at g of c, then the composite function given by f of g of x, or f of g of x, is continuous at c. The limit as x goes to c of f of g of x is just f of g of c. So describe the intervals on which each function is continuous. We have f of x equals secant x. Well, secant x equals 1 over cosine x, right? So where's cosine 0? It's 0 at pi over 2, 3 pi over 2, 5 pi over 2, and so on. So secant x then is discontinuous at pi over 2 plus n pi. So it's continuous on the interval from negative pi over 2 to pi over 2. I should do parentheses because at those points is not continuous. And then from pi over 2 to 3 pi over 2. From 3 pi over 2 to 5 pi over 2. From 5 pi over 2 to 7 pi over 2. How about the next one? G of x is cosine of 1 over x when x is not 0, because that wouldn't be defined, at x, x equals 0. This graph would look something like this. It's coming in and do this zigzaggy thing. So this is continuous on the interval from negative infinity to 0, and then from 0 to infinity. At 0, I mean, this part here, we just don't know what's going to happen with it. At 0, you have 0, but this is jumping all around. So the first part, the limit of cosine 1 over x, that's just not going to have a defined limit. H of x equals x cosine 1 over x. And when x is not 0, and it's x when x equals 0. So it's just 0 then. Well, consider this. The negative absolute value of x is less than or equal to cosine x. Let's just say cosine of 1 over x. Less than or equal to the absolute value of x. What's our limit as x goes to 0 of the negative absolute value of x? That's just 0. What's the limit as x goes to 0 of the absolute value of x? That's also 0. So, by the squeeze theorem, the limit as x goes to 0 of x times cosine of 1 over x equals 0. And I should have an x in here, x times that. I mean, it's reasonable to say that negative 1 is less than cosine of 1 over x less than 1. So if you multiply everything by x, you get the same thing. Okay. Let's go on to our last page. This is something you've seen before. So pause if you need to pause. The intermediate value theorem, I'm sure you've seen this in pre-calculus, especially if you had pre-calculus with me. I know you've seen it. But I would expect any pre-calculus instructor would teach the intermediate value theorem. If f is continuous on the closed interval from a to b, and k is any number between f of a and f of b, then there's at least one number c in the interval such that f of c equals k. So what we saw before was that if it crosses the x-axis. So this is similar to that. So here's your a, f of a. Here's your b, f of b. There must be some number k between f of a and f of b such that there's a c in between a and b equals f of k, or equals f of c equals k. So explain why the function has a 0 in the interval from 1 to 2. And the function I forgot to type in here, f of x equals 1/16 x to the 4th minus x cubed plus 3. Well, f of 1 is 1/16 times 1 to the 4th minus 1 cubed plus 3, and that's going to be (2.0625), and that's positive. F of 2 is going to be 1/16 times 2 to the 4th minus 2 cubed plus 3, and that's going to be -4, and that's negative. So since f of 1 is positive and f of 2 is negative, there is a value c where, let's see, 1's less than c less than 2, such that f of c equals 0. That'll do it for 1.4. Hope you enjoy this section. Hope it's not as stressful as what we saw in 1.2. And 1.5 should be good as well. So send me your questions, and I will talk to you guys later. Thank you.